Okay, cool. Thanks for coming to the review. Today I'm going to be talking about lecture 5, which is light and quantum theory. And so first thing, just light as a wave. Up to this point, light had generally been accepted as a wave. So you have like the two oscillating directions that are both perpendicular to each other. So you can think of it in kind of like a 3D way. This is where we get the term electromagnetic radiation, just that idea that it's radiating in those different directions. And then the properties of the wave, we have our nodes, which are just the zero energy point on the axis of the wave. The amplitude is going to be from the node to the peak of the crest or to the peak of the trough, either way, whichever is easier to think about for you. And then a wavelength is just the distance from the same point on the wave, which we'll talk about here on this next slide. So to measure light is just going to be the distance from crest to crest. So you can either think of that as like, get a brighter color, like from here to here, for example, or here to here, like here up to here, right? Because you go this part of the wave and that part. And you can see here, these two are obviously bigger differences between the waves. So this one would be a much higher energy, and this one would be lower. Because the distance between the waves tells us how high the frequency is, and a high frequency, right, the number of wavelengths passing through a point per like second or another unit of time is going to give us more speed, which in turn gives us more energy. It helps us determine how fast a light wave is moving, which is useful for other things later, and it can tell us about the absorption and emission spectra. So here's the atomic spectra. We have our radio, microwave, infrared lights, and then this rainbow section is our visible light. We have our UV, X-rays, and gamma rays. We know that this side is going to be the lower energy, because just looking here at the frequencies and wavelengths, we can kind of compare them and say, okay, this one is going to be 10 to the 4th hertz versus 10 to the 24th hertz. Much higher frequency, so that's going to be higher energy as well, because we know that those two things are proportionate. And then another thing I would remember from this slide is just the range of visible light. So that's 400 to 750 nanometers, which is useful in case they ask you on a test, if you'll be able to see a certain wavelength in, the visible light range or whatever. I know there was a question like that on exam 1. So yeah, just brush up on that if you feel like you need it. Another thing to remember, all light waves travel at the same speed, which is this value here, 2.99 times 10 to the 8th meters per second. And we can use that in this equation and a lot of others, where we know that the speed of light is equal to the wavelength times the frequency, just to be able to solve for each other there. Okay, so then here we have just a quick little practice problem. So okay, so typical microwave oven. Okay. A typical microwave oven operates at 2.45 gigahertz. Calculate the wavelength of this electromagnetic radiation. Okay, so you can see here that I have this relationship set up, the C equals wavelength times the frequency. And so we're just going to put in the speed of light for C right here. And then we don't know the wavelength. That's what the problem is asking us for. So we just put the lambda sign right here. And then we have the 2.45 gigahertz. And then we want hertz to be our unit, because we know that 1 hertz equals 1 second, and our typical unit for frequency is going to be this meters per second unit. And we can see here, oh, sorry. We can see here that our seconds are on the bottom. So an inverse second is going to be exactly what we need for the problem. So that's why we're going to convert to hertz here. So we're going to do 2.45 gigahertz times 1 times 10 to the 9th hertz over 1 gigahertz times 1 second over 1 hertz. We'll allow these units to cancel out, and then we'll get it in meters per second. If we go ahead and put that in the calculator here, we will get times 1 times 10. And then, so we're going to get this lambda equals 2.45 times 10 to the 9th. And then we'll have that. Sorry, I'm just going to be lazy and write 3 times 10 to the 8th. And then we'll go ahead and divide this over here. This is going to be in seconds. And then 45 times 10 to the 9th seconds. And then, perfect, 3 times 10 to the 8th divided by that big number. Let me put that in here. That's going to give us, so these units will cancel out. We'll get 0.122 times 10 meters, but that's not quite what we want. So we're going to go ahead and actually convert that to centimeters, because in the context of this problem, it's a microwave, right? And 0.22 times, 0.22 meters isn't really useful for us to know, exactly how big that's going to be inside the microwave. And so for this particular problem, we're going to go ahead and put it in centimeters because that will give us a more relative number there. So that is how you would solve that problem. And I think on the problem set, it also asked to figure out like how many nodes of the wave would be able to fit in the microwave. And so to figure that out, you would just go ahead and just do the problem, take the total length of the microwave, divide it by this length of the wave, and that will tell you how many wavelengths for that problem. I think it's off of problem set 5 or 6 if you want to go back and look at that. Anyway. Okay, our next thing is kind of the unsolved mysteries that this whole light wave knowledge was starting to open up because classical physics is going to explain these things. Black body radiation, like why certain objects emit light only at high temperatures, the ultraviolet light catastrophe, and then the photoelectric effect. Okay, so first thing here, a black body is something that absorbs all radiations of light at all wavelengths at room temperature. So like if you were to shine like a light on it, or like, I'm trying to think how to explain this. Like if you were to look at, I guess it's heat signature, you would just see it black because it's constantly absorbing light. It's never emitting any, which is when you would start to see like color coming off of it. And this was a problem because if an object is constantly absorbing radiation, the object is going to keep getting hotter and hotter, and the room is going to keep getting colder and colder, right? Because all of the heat from the surroundings is coming into the system, and it's like holding all that heat. It's never getting any back. And so that contradicts the second law of thermodynamics, which tells us that the change in entropy should always be greater than 0. And so to try to figure out what had happened, scientists at the time had just discovered like a perfect absorber where if they had like just a box, they would punch a hole in the side of it, and then like the waves going into it would just keep bouncing off that hole, so they would never really like escape because the hole was too small for them to fit inside. And so they would constantly be like hitting it, and it would be like a perfect absorber because it would always be going. And so they did the reverse of that with an emitter. And so they took a really hot oven, punched a hole in the side of it, and then as those waves would try to escape, because like the oven's really hot, right? The hot waves want to get on the outside where it's cool so they can try to reach equilibrium that way. They would keep bouncing off of it because it was too small. And so they could use that to measure how much radiant energy was emitted in each frequency stage. And what they found out was that there was this pattern for visible light, right? Like for each of the colors, as the radiation grew intense, like it would come up to this point and then it would go back down and go back down. And so that led them to another question, which is the ultraviolet catastrophe here. Like, why do bodies radiate the way they do? Why do they have that peak and then start coming back down? Like, because the relationship at classical physics, like if this is the intensity, right, and this is, I think it was frequency. Yeah. There's a frequency here. So classical physics had it going like that, but in all reality, it went like that. And so they were asking, why is it like that in real life? And basically what they found out was when Planck came along, and he set up this equation right here, where he said, okay, well, this isn't happening, right? Because at these higher levels of energy, like the particles don't have enough energy to emit anything at that high. So that's why they reach this peak and then they start to come back down. So he set up this relationship where he came up with a constant for each frequency. Then they would get up and multiply by this constant to basically say, okay, like at this energy level, this is how much how much radiation is going to be emitted, and that's it. Because eventually it will cap out. So that led him to talk about the quantization of energy, which says that objects absorb and emit energy in specific quanta. Energy is proportional to frequency, not intensity or amplitude. We've seen this little diagram before where basically you have these places, and it takes more energy to jump up from the ground state to, the n equals 1 level. And here's the n equals 2, n equals 3, n equals 4, and then way up here somewhere is like n equals infinity. And the distance between these just keep like getting closer together. But they can't, the thing is that the electrons, like they can't exist right here. They have to be exactly on the level that they're going to, right? It's kind of like this game, right? The ground equals lava, or the ground is lava, where you can't be on the ground because you'll burn up and die if you go there. It's not like that for electrons, but basically they're just not allowed to go in these areas. They have to be either on 1 or 2. Level 1.5 doesn't exist. They can't go there. Okay, the photoelectric effect is just kind of going along with that, the observation that electrons are emitted when light of energy, like super high energy, shines on metals. They noticed that for every metal, this was different. So it was unique for every thing. And this is where we get the idea of the work function from. So it tells us that the low frequency light, there's not going to be any electrons getting emitted, or if it doesn't reach like a certain threshold value, then you're not going to see electrons emitted either. And as you get more intensity, then the number of electrons is going to increase. Okay, so then we have a little practice problem here where, let me go ahead and get this set up. I don't know what's going on with my camera here. Okay, perfect. Okay, so they give us that we're looking for the wavelength, right? And so then they give us the work function here. And then they give us a conversion factor from electron volts to joules, which we always want to be in joules when we're talking about energy because that's going to be our SI unit. So I'm going to start here by going ahead and converting my 4.3 electron volts to joules. It's into the negative 19th joules. And that's going to give me 6.88 joules, it looks like. Cool. And so now I can take this and plug it into this equation that I've got here at the top. So this is going to be my work function. So I can go ahead and do 6.88 joules equals H, which we know is 6.62 times 10 to the negative 34th. And the unit for that is joule seconds. And then for frequency, we don't know that yet. So the first part of this is we're gonna go ahead and solve for frequency here. And so I'm gonna just divide off my H. Awesome. And so then these units are gonna cancel. We'll be left with amperes, seconds, or hertz. Okay, and so then that will give me 1.039 amperes seconds. Here's my frequency. Awesome. And then next we can go ahead and take this and for this C equals this equation, right? And we're solving for wavelength now, so we're gonna just rearrange that a little bit, and then that's gonna give us this wavelength equals that equation here. And so we're gonna go ahead and plug in our C value, our meters per second, and then our frequency is gonna be this seconds right here, and then we're gonna get 2.99 times 10 to the 8th divided by 1.039 here. And that's going to give us this really big number. And so to go ahead and, because I'm going to want it in nanometers, just because usually when we get our wavelengths, they're going to be big numbers in meters. And so again, nanometers makes it a little bit more of a comparable good value for us. So what we're going to do is these will cancel out here as well. And so I'm going to say that for every 1 meter, I need 1 times 10 to the 9th nanometers. And so that's going to give me, or negative 9th, excuse me, times 10 to the 9th nanometers, or no, 26. Sorry guys, bear with me. Okay, so let me go ahead and put that in here again. And so that would give us 287 nanometers, or you can do 287.78 nanometers. Okay, and so then we're going to go in here. This is going to be the longest wavelength of light that can eject, right? And so just looking at this, if we go back here to this atomic spectra, we can know like, okay, well, this isn't going to be the visible light range because it's less than 400 nanometers, for example. So that would be how we could do that. Okay, and then that is everything that I have for you guys. So if you have any questions, probably email your TA or something, but you can always email me too. And I hope everybody has a great day.